Hello, I'm Cameron Paul, and I'm here with Anson Marathu to present on the vibrations found in wind turbines, as well as the methods implemented to mitigate the effects of vibrations have on wind turbines. The demand for clean, renewable energy has been growing for decades. As non-renewable resources diminish and a climate crisis seems imminent, efficient resources of renewable energy become ever more important to obtain. One of the most promising areas of renewable energy comes in the form of wind power. People have been harnessing the power of wind for generations. As our technologies have advanced, we have built larger and more efficient power harnessing systems, including large-scale wind turbines. Due to the scale of these turbines and the nature of the semi-unpredictable wind forces they experience, vibrations occur and can reduce efficiency in power generation. The focus of this presentation is large-scale wind turbines and the methods used to dampen vibrations that occur in them. Vibration control in wind turbines can be organized into three categories: control strategies, control dampers, and system controllers, as seen in the chart. All of these control methods work together to mitigate vibrations. There are three vibration control strategies: passive, active, and semi-active. The goal of these control methods is to maximize the performance of wind turbine energy generation by minimizing the vibrations of the wind turbine drivetrain and tower. Damping devices are generally used for energy dissipation. There are many types of damping devices that have been implemented for structural vibration control, but we will only be focusing on tuned mass dampers and tuned liquid dampers. Finally, system controllers play an important role to maximize the overall performance of the system. Because most wind turbines are extremely tall and are placed in areas of turbulent, high wind speed, high vibration occurs at the top of towers and in the blades. Horizontal axis wind turbines in particular also experience extreme problems with vibrations due to the heavy loads on top of the tower, which includes a generator, gearbox, and other installation kits. Wind excitation, earthquake excitation, and waves for offshore turbines are major sources of structural vibrations. There are two primary types of vibrations that are induced in the blades of the turbine: flapwise and edgewise. Flapwise vibrations occur out of the plane of rotation of the blades, and edgewise vibrations occur in the plane of rotation of the blades. As mentioned before, there are three types of controls. Passive control systems consist of a series of springs and dampers and require no external forces. Passive control is capable of enhancing the structural damping, stiffness, and strength of a wind turbine. For active control systems, external forces are applied to counteract vibrations. Both active and semi-active control systems employ external controllable force devices with integrated sensors, controllers, and signal processing. Generally, we see implementation of the semi-active control systems for maximum efficiency. The next couple of slides will go over the various damping systems that utilize active, passive, and semi-active control systems.
Tuned mass dampers consist of a satellite mass with spring and damper components placed in relation to the primary mass, which in this case is a wind turbine. It provides a frequency-dependent hysteresis characteristic that increases damping in the main structure. This helps to dissipate energy from vibrations in the turbine. They have been used in many systems, including tall buildings, bridges, and wind turbines. In many studies, a Fourier transform approach was implemented to find the displacement at the top of the tower. The wind turbines were modeled as multiple degree of freedom structures, and various wind loadings were simulated. Studies found that the passive control approach was extremely effective and that the effectiveness of passive systems can be further improved by utilizing elements of active and semi-active control systems. Tuned liquid dampers consist of a U-shaped tube filled with liquid attached to the main structure. When excited, the liquid, acting as the mass for the damper, oscillates in the tube and absorbs the energy from unwanted excitations, re-establishing the system to equilibrium, similar to a pendulum establishing equilibrium in extremely tall buildings. A tuned liquid damper is typically placed at the top of the structure. Studies found that tuned liquid damping is effective for small and large vibrations and can reduce vibrations in wind turbines up to 55% compared to turbines without liquid damping. Active control can be applied through either of these two pathways. In feed-forward control, calculations are made based entirely on the input excitation to the system, and the vibratory response is mitigated by forces determined from these calculations. In feedback control, the output response of the system is also evaluated, and the control inputs are adjusted to minimize any measured error from this output. The feedback control method is optimal to encompass and mitigate more of the vibrations experienced by the structure. In conclusion, we believe that wind turbines are a great source of renewable energy, and that further research and development into making wind turbines last longer and be more cost-effective is a great start to propel them into becoming a more prevalent energy source. We hope this has been informative, and we thank you for your time.